Swayam Prabha. Digital India. Educated India.
So today we are going to start a fresh topic called Markov chains, and this is continuing our study of random processes. So when we have already defined what is a random process, and in that so far we said that okay, in general stochastic processes are complex to describe if you want to describe them in generality, because you need to give finite dimensional distributions of this process, right, which involves you to give joint distributions of n number of random variables in that process, where n could be any number, right. So a complete characterization of a stochastic process is complicated, but we saw that one simplest process we mostly dealt with was IID process, independently and analytically distributed, and that process was very easy to describe. All you needed to describe is just give one distribution, that is the common distribution that each of the random variables are following. So, and from that you could characterize all the finite dimensional distributions. But like IID process could be restrictive, right, it is not necessary like every time whatever you are doing, like when you have defined something as a process, it is not necessary that every time what happens today is going to be totally independent of what happened the previous day, or what is going to happen tomorrow is going to be totally independent of what happened today. So IID process basically tried to model something which did not have any memory in that. Like I can say that okay, whatever is going to happen tomorrow is going to be independent of what happened today, and what happened today is actually totally independent of what happened yesterday. That means they are independent in a way, also they are not carrying memory. So what happened previously is not going to affect me or the things that is going to happen in the future. But often in reality we will see that what happened today can have some impact on tomorrow, right. Let's suppose let's say the weather is going to remain let's say very hot for few days, you won't expect weather to suddenly go and start raining the next day. Like some kind of effect you expect that what happened today is going to impact tomorrow. So then we want to bring in some aspect of memory in our stochastic process, and to do that Markov chains come to our help, and we are going to describe what we mean by Markov chains today. And we will be focusing on discrete time Markov chains. Okay, if for all okay. Okay, so this is the definition of discrete time Markov chain. So we are going to take a process xn which takes value in a countable set S. What does that mean? Each of these random variable xn, their outcome lie in a countable set. Okay, and this countable set, the elements in this countable set, we are going to call 1, 2, 3 like that. We index them. Since this is countable, we can index like that. Now this process, this stochastic process, we are going to call it as discrete time Markov chain. If you are going to take the values, okay, I0, I1 all the way, any values that belong in my set S and another J, and it so happens that given that the x0 random variable took value I0 and all the way up to xnth random variable took value I, that has happened already, and now you ask the question, in the n plus 1th round I take the value I. If this probability is just equal to this, that is, it only depends on what is the current one, xn equals to I, what is the state you took, and the question that you are asking that it goes to state value j in the next round is independent of all the value it took previously. So we are going to take the value taken by these random variables as the states of this Markov chain. Okay, so every x1, x2, x3, they are all taking values, right, and we are saying each one of them are going to take a value from this countable set S, and we are going to call this as set of states, and these states are basically, we can index them 1, 2, 3 like that, continue the count. Now what we are saying is, given any, let us say my process has evolved and it has taken these possible states, that is my x0 it took state I0 and x1 took state I1 and xn minus 1 took state In minus 1 and xn state took I, let us say this has been observed, and now I want to ask the question, okay, what is the probability that in the next state, sorry, in the next round I am going to take the value or I am going to take the state I. If this depends only on the current state you are now currently at and independent of the what has happened so far, then this process is going to be called as DTMC. Okay, now yeah. No, this is J, sorry. Okay. Now what we are going to call this quantity, let us say I am in round n, I am going to call that as present. Let us say the process has evolved, I am on some particular day, nth day, let us call that as present. So I am saying, okay, I have been observed that, it has been observed that on day n or today I have taken the state I, so this is like my present, and previously till yesterday My states are I0 and all the way up to IN minus 1. This I am going to call it as past. And now this is my tomorrow, and this I am going to call it as my future. So what is basically this probability saying this? Future, given all the observation till today, only depends on my today, it does not depend on my past. Okay. So if this quantity holds, then we are going to call this as a DTMC. So you see that this process has some kind of memory in it, right? What happens tomorrow in the future, it's going to depend at least on today. It's not like it is even independent of that. So had it been, if this process has been an IID process, what this would have been? Yeah, it will be simply probability of xn plus 1 equals to j. It would have been not even dependent on my present, right? Forget about the past. So when this property holds, at least there is this kind of memory in this, then we are going to call this as Markov chain. So here discrete time should be obvious because we are indexing time that are discrete valued. I am only counting 1, 2, 3 as like a time index. These time indexes are not continuous. Okay. So most of the courses in this course we will only focus on this kind of discrete time Markov chain, and if time permits later we will touch upon continuous time Markov chains, okay, where my time could be continuous. Okay, so instead of this n to be taking only some integer value, it could be taking any value in some interval. So basically what this is saying is, my process x0, x1 all the way up to xn minus 1 is independent of x1 plus 1 given xn. So as I said, this is my past, this is my future, and this is my current status. So my past is going to be independent, my future is going to be independent of the past given my current. So because of this nature, if I want to understand what is going to happening in the future, I only need to know where I am currently now. That is the only thing that is going to impact my future. So I don't really need to know what happened to me so far, right? I can ignore that because that is not going to affect what is going to happening, how the things are going to happen in the future only depends on where I am now. Okay, so x0, x1 all the way up to xn minus 1, this is my past. I am going to just call this entire thing as past. This all the past is going to be independent of my future given this. So processes also discrete and random variables are also discrete. The process is discrete because you are indexing them with discrete time, right? And my process is discrete valued because I am saying that this is it is taking value in a countable set. That is why this is also going to be discrete here. Okay. So okay, now let us take xn is an IID process, okay, and such that this guy xn equals to 1 and we are just going to say okay, this is going to probability P, and where Sn belongs to xn belongs to 0 1 for all n. So let us take the sequence of random variable where each xn is taking value to be either 0 or 1 and it is going to take value 1 with probability P. So you can think of this as a sequence of coin tosses where whenever it comes heads you are going to take it as 1 and whenever it comes tails you can take it as 0 and probability of head coming up is P. And this is obviously a Markov chain because it is we are telling it to be high ID, so it is already going to satisfy my Markov property. Now let us define another process for all n, okay, yeah, xi for IID. So if my process is IID, I am saying this xn is satisfying this Markov property.
Would the future is even not dependent on current and future are independent?
Yeah, so what? So then we are saying what we want this property to hold, right? So if my process is IID, xn plus j is anyway this, like, and this is going to be simply x of n plus 1 equals to j, whether you condition or uncondition does not matter, right, for an IID process. So what I am saying, so for an IID process you need to check this condition holds, right. For an IID process probability that xn plus 1 equals to j, given this it is going to be simply xn plus 1 equals to j, but this itself is again this, right. How? If it is an IID process, if it, because xn plus 1 equals to j is independent of xn equals to I, this is the meaning of independence, right. So that is why this Markov property is trivially satisfied for an IID process. Okay, now let us take this yn, which is nothing but summation of n, this random variable. Now we want to ask the question whether this yn satisfies a discrete time Markov chain. So first of all, is this yn is going to be IID? So okay, let us say I can write it as, so if I have written it like, I could also write it as yn minus 1 plus xn, right. I just separate out the first n minus 1, by my definition that sum is yn minus 1 plus x. So yn depends on previous yn minus 1, right. So this feature is not independent of my current state. So this yn plus 1 minus 1 and yn, they are no more independent, right. So this sequence is definitely not independent. So then let us see whether this satisfies Markov property. Okay, first let us first count what is the value taken by yn. What is the value taken by yn? So each of these xi's can take value 0 or 1, right. So what is the value taken by yn? It can take a value all the way up to 0 to n. So and for n sufficiently large, it can take all possible values of n, right. So as I let n go to infinity, I mean each of these yns can take. So I could, that is why I could set yn belongs to s, I can say where s is simply 0, 1, 2 all the way up to n. So instead of just saying yn belongs to 0 to n, like that I am just writing one value where yns is taking all the values from for all n. So now let us try to understand what is this probability. So let us say I want to take some for some ij, so I want to take this set of, right, let us say I have some I1 up to in minus 1 and I that belongs to S, and I will take another j belongs to S, and I want to compute this, that y0 equals to I0 I want to compute this. So let us see what is this value. So I have written yn as yn minus 1 plus xn, but I could then this is also say true that yn equals to yn plus x n plus 1. Okay. Okay, now let us try to understand. So what is, now let us this is just a relation. So now let us try to compute this. What is this value is going to be? Suppose I know that if yn is going to be some value I, what are the possible values of yn plus 1? Yeah, either it is going to remain at I or it can take the value I plus 1, right. Suppose now let us say if this guy j equals to I, what is the value of this probability? One minus p, right, because that means tail must have happened, because of that x n plus 1 is 0. Okay, so that must be 1 minus p. And if this j equals to I plus 1, it should be p. And for any other value of j which does not belong to I plus 1, what could be the value? Any other value, just so I have been told yn equals to I, let us take j is equals to anything other than these two values. Just let us take j to be I plus 2. Can yn plus 1 be I plus 2? No, right. Can it be I minus 1? No, right. And can it be any value other than I and I plus 1? So then this is going to be 0. So this value, to compute this, what I needed to know, what is the current value of yn, nothing else I needed to know, right. So because of that, can I write, so these guys are immaterial. To compute this, I only need to know what happened at I only need to know what is the value at yn. So then is this a discrete time Markov chain yn? Yes, right, because this exactly satisfied my condition here. Okay, fine. Now what we basically showed is, in this yn plus 1 was basically yn minus 1 given yn. So like see yn plus 1, earlier I had said that this x1 plus 1 was independent of all this, but you can take one at a time in this. This yn plus 1 was independent of yn minus 1. As long as you know yn, nothing behind it are useful to me, okay, provided I know what is the value of yn. So we are saying that yn plus 1 and yn minus were independent, but this independence is conditional. Conditioned what? Conditional that I know what is the value of yn. But if you just try to, but this does not imply that they are independent unconditionally. So if you just ask are yn plus 1 are independent of yn minus 1, is this true? Without conditioning on yn? No, right? Because if I know yn minus 1 takes value I, what could be the possible values of yn plus 1? So suppose let us say this value, this realization took value I. What are the values of yn plus 1? It can remain at I or jump by one value or jump by two values at most, right. So in that way if I know this, I already know about this, so they are no more independent. But if I know what is yn, then they are independent of each other. Okay, so as of now we said that Markov, the way we define Markov property, it kinds of implied that Markov property is just talking about one step memory, that the next step is conditionally independent of everything past given the present one. What about further steps in the future? So let us say if I know something tomorrow, today I know tomorrow is going to be independent of my past given my Markov property, but does this also imply that given today my day after tomorrow is also going to be independent of past? Okay, is that true? I mean, do you feel that by Markov property that should imply? If tomorrow is going to be independent of my past given today, is day after tomorrow is also going to be independent of my today given my past? Yes. Okay, let us formally verify that. And that is true, like all my future steps, however further they are going to be independent of my past given my current state. So we are going to state this formally. So let us first try to digest these notations because we are going to use this notation again and again now in the study of Markov chains. So let us take n, when I write n it will be usually meaning my current index, my present, and when I write this n1, n2 which are indexes in the future. So suppose n equals to my current day, let us say it is the 10th day, n1 could be 12th day, n2 could be 15th day, like that. They are the indices in the future, and then I would write this I0, I1, In minus 1 till I to denote these are the states taken in the past. That is, on x0 took the value state I0, x1 took state I1, xn minus 1 took state n minus 1, sorry In minus 1, and on my current day nth I took the state I, and then these are my futures. in my future date, in my next n1th n1 indexed random variable, I am going to take state j1 and all the way, let me also call this as nm, and in that nmth date I am going to take state jm. So this is the notation. So at time 0 I took state I0, at time n minus 1 I took state I n minus 1, and the current time I took state I, and in the future this n1 which is larger than this n, I am going into state j1, and after that I am going into state j2 in n2 which is larger than n1, like that all the way up to nm. So what I am looking is, from my current time I am looking at m steps in the future. I mean these steps are not immediate m step, they could be at some point in the future, that could be n1, n2, n2, like if I am in day 10 it could be 12th, 15th, 16th, like that, if I am looking at 3 points in the future. Now it is all it is saying is, this past again does not affect this feature probabilities given my current state. Okay, so far my DTMC, by the way I have defined it, it just said that it did not worry about all this, it only worried about n which was n plus 1. Now if I am saying, okay, if this n1 could be larger than n, larger than n plus 1, and also if you look at all the things that you are going to look into the future, that is going to be independent of this. So if your stochastic process is DTMC, this is also guaranteed. Okay, let us see why this is the case. So I am going to do it for, but I said I am already in today's. That is what I am saying, right? By what I am saying, today I know and I am asking about tomorrow. If you want to assume that today also I do not know, then go back to the previous day, maybe you know about previous day and ask for today, and the same definition applies. And whatever you want also, like fine, if you do not know today, you will know about yesterday, you can go and do the same thing here. If you remove this part, no, it does not hold. This is true if you know what is today, what has happened, then we are saying future is independent of the past. Now okay, so suppose you are saying this is not there, then it should be n minus 1. This will be my latest information, right? This will hold. We will find the, no, this is like whatever, like he said instead of Aaj I only know till the previous day, let us say, but I have to assume that that state is I here. In that case this is about future, right? This is still going to be independent of my previous days, all the one from n minus 2, n minus 3 till 0. So whichever, so basically what it is, you have some information till some point and after that you want to ask about future. Now whatever information you have, to know about the future you can take the latest information in that and throw away all the others. That is what our DTM Markov chain is telling. Okay, it need not be like till today and everything. What? So the generally I have to see that whatever information I have, only the latest matters affects the future, and fast I can just throw. Okay, so what I am going to do is I am just going to do it for a special case, and that will give you the idea how this should be done for rest of the for how that can be generalized to this case. So I want to now do it for this case. X n plus 2 equals to j given x naught is equals to I naught, x n minus 1 equals to minus 1 and x n equals to I. So now I am basically asking tomorrow, I am asking for day after tomorrow, okay, whether probability that my what happens day after tomorrow is conditionally independent of what happened so far given my today. So how to show this? How to show that this is equals to this, okay. So then if I can show this, you could also extend that and say that okay, even for the future this can be applied. Now how to do this? So let us take this, I am going to write it as is this correct? So this is like conditional probability, right? Now what I have done is I have added this xn plus 1, but now I am allowing it to take all possible values. Xn plus 1 can take value k, and now I am allowing this k to take all possible values and then summing over it. Then is that this is equals to this, right? So what I am basically doing, let us say I am in this, where this is x n plus x n state and this is x n plus 2, okay. So basically here it was asking okay x n पे I था, now I want to go to x n plus 2 equals to j. This is today and this is day after tomorrow. So before you reach day after tomorrow you have to go through tomorrow, right? Let us say this is tomorrow, and now tomorrow can be any of the possible states in S, right? So I am allowing it, okay, you go through tomorrow through whatever possible state, and then if I do this, then so basically I am going from here to here and I am allowing all possible routes, that is different possible values of k. So that is why this probability should be equals to this, okay. So now let us so after writing this, let us go back to our initial things we studied, how to split these probabilities. I am going to split this probability as x n plus 2 into, okay, maybe first this x n plus 1 equals to j k given x naught. So I am just simplifying this, into probability that x n plus 2 equals to j given x naught I naught all the way up to x n minus 1 equals to I n minus 1, x n equals to I, and x n plus 1 equals to k. Is this correct, the way I have split the probabilities? So I am just doing probability that A and B is nothing but probability of A into probability of B given A. So I am just taking this as event A and this as event B. Okay. Okay, now let us try to apply our Markov property to each one of these terms. Now I am asking probability that I am going to take state K tomorrow given I am in state I today, and I am going to take state J day after tomorrow given that tomorrow I am in state K. By Markov property this should be into probability that x n plus 2 equals to k given x n plus 1 equals to k. X, okay, what is J? Okay. So now what is this telling you? Okay, now you go back to this probability. What it's saying is you from today you started in state I and you went to state K tomorrow, and then tomorrow you are already in state K and from there you go to state J day after tomorrow. If that is correct, like if I sum it over all these possibilities, so this is basically asking this question, right? I start from I today, I go to some state K tomorrow, and from there further I go to state J day after tomorrow, and now again I am looking into all possible routes. So this should be exactly equal to x n plus 1 equals to J given x, sorry, 2 equals to J given x plus 1 equals to R. Xn equals to, right, equals to R. So what it is saying is that what happens day after tomorrow only depends on today, okay, and I can forget what happens till yesterday. Okay, fine.